All right, let's finish that example that we were talking about. So we had two vectors 2, 1, 1 and 1, 2, 3. So let's call this one V1. Let's call this one V2. And we saw that they span a plane. That's because these two vectors were not parallel. If they were parallel, then they would span a line. And one question that we can ask is, how do we describe this span? So how do you describe the plane in terms of an equation? So one question we could ask is, under what conditions is the vector ABC, let's just say you have a random vector in R3, under what conditions is this in the span of V1 and V2? For example, if you do V1 plus V2, you get 3, 3, 4. Right? That's in the span. Or you could do 2V1 plus V2, and then you're going to get 5, 4, 5. That's also in the span. And so the question is, what do A and B and C have to do in order to be in the span? And we saw that there are some vectors that are not in the span because the span is a plane. So any vector that's not on that plane is not in the span. Right? So another way of phrasing this question is that we're looking for an equation of the plane. We're looking for what A and B and C have to, what equation has to come true in order for this vector to be on the plane. Well, remember, in terms of linear equations, in terms of a system of equations, how can we rephrase the fact that ABC is in the span? It's in the span if this vector is a linear combination. So let's call this vector W. If it's a linear combination of V1 and V2. And that can be, how do you write this in terms of the augmented matrix? So if you have 2, 1, 1 and 1, 2, 3, and then augmented by ABC, if the corresponding system of linear equations, so in this case there are how many constants, how many coefficients will there be? 2, right? C1 V1 plus C2 V2. So if it's possible to solve this system, then ABC is in the span of V1 and V2, otherwise it's not in the span. Okay, so what should we do? We should row reduce. Right. So let's swap. What should we do first? We could swap rows 1 and 2 to get a 1. And now we need to row reduce. So we have a pivot here, and then we need the numbers below that one to be 0. So we can do row 2 turns to row 2 minus 2 row 1. It looks like you're going to get 0 minus 3 and then A minus 2B. And then we can do row 3 turns into row 3 minus row 1, so it'll be 0, 1, C minus B. Okay, and again we can swap rows 2 and 3 to get a 1 because we're done with the first column. So this, and then one more step, we can do row 3 turns into what? Row 3 plus 3 row 2. So you get this, and then so 3c minus 3b, and then you add it, so you're going to get a minus 5b minus 3c. So this is the, we got the, we got the echelon form of this augmented part, and so we have this. So now from this, under what conditions is the vector ABC in the span of V1 and V2? We see that ABC is in the span of V1 and V2 when what? Well, it's when the system that corresponds to this augmented matrix has a solution. And so when is that? If you look at the third row, you need A. What has to happen with A minus 5B minus 3C? It needs to equal 0. It needs to equal 0 because if it's equal to 0, it needs to be equal to 0 because if it's not 0, then the system will not have a solution because you have 0 and the you'll have zeros here, but then a non-zero number here, and that'll have no solutions. So you need A minus 5B minus 3C to equal 0. If it is equal to 0, right, then the third row doesn't tell you anything, but you look at the first two rows, and then you see that you can solve for C1 and C2. So that would mean that ABC is in the span of V1 and V2. Okay. So it's in the span when A minus 5B minus 3C is 0, and if A minus 5B minus 3C is not equal to 0, then it's not in the span. And so that makes it very easy to see what, to come up with vectors that are, okay, I really don't like this aspect of this app because it's extremely, anyway, it's easy to come up with vectors that are not on the plane, right? So you just need to come up with, so for instance, how about 1, 2, 3? Is that in the span of V1 and V2? Well, no. Because 1 minus 5 times 2 minus 3 times 3 is not equal to 0. Okay, and so let's conclude what the span of, so the spans of, let's say you have just k vectors, right, in R3 is either what? Well, first of all, it's the 0 vector if all the vectors are the 0 vector. Then what's the next possibility? It could be a line if all the vectors are parallel. Right? If they all happen to lie on the line, then the span is a line. Or it could be a plane. And what's the other possibility? It could be R3. That's if you have 3 vectors that would be, so let's say that you had 3 vectors in R3, right? If the first 2 are not parallel, so if there are 2 non-parallel vectors, and then the third one is not a linear combination of the first two vectors, then the span will be R3. If you have three vectors and two of them are non-parallel, then you're definitely going to get a plane. And then if the third one is, right, if it is a linear combination of the first two, you get a plane. So you get at least a plane, but if it depends on what the third vector is. I mean, if the third one is a linear combination of the first two, then the span doesn't get any bigger, and so you just still are left with a plane. But if the third vector is not in the span of the first two, then you span more things, and so you get R3. So hopefully this gives you some intuition about the span. The span is never going to look anything like a sphere or some kind of oddly shaped thing, right? I mean, the smallest span is the origin. Then the next smallest span is an entire line. You know, you're never going to get like a line segment or anything like that. It's always a full line. And that's because when you're, doing the span, you have positive and negative real numbers, right? So you kind of have to get the whole line. And then the next smallest is a whole plane. And then the next smallest span is like a three-dimensional thing. So we haven't gotten into the technical definition of dimension, but hopefully that gives you some intuition for span. And so yeah. So now, I mean, one thing that our discussion is leading into is this notion of linear independence. So for instance, if you have, 5 million vectors that lie on the same line, right, the span is still just this one line. So it's not how anyone would describe a line. That's you would give all these vectors to happen to lie on a line and say it's that span, right? You would just pick out one vector and then say it's the span of that one vector. And similarly for a plane, you would say it's the span of these two, non-parallel vectors. You wouldn't give like 5 vectors on the same plane and say it's the span of those 5 vectors. So that leads into the notion of linear independence, and that's what we're going to talk about next. Okay.